All right, welcome to lecture. We'll get started here in just a sec. Continuing on in chapter 8, where we left off, talking about molarity. And again, like usual, if you have questions, feel free to ask them below in the text box there. And again, we'll get started in just a second. Okay, so we are talking about molarity here. We're talking about solutions, is sort of where we left off. We're talking about concentrations, and we left off talking about molarity. And molarity, again, a reminder, is moles per liter. And it's the most common sort of unit of concentration that we have. Is the one we see a lot, on bottles that you use in the lab. Big M is that moles per liter. And we also talked about some percentage, I think, concentrations as well: percent mass, percent volume to volume, percent mass to volume as well. But out of all those, really, molarity is the one that you come to see the most often. And again, you think of molarity almost as a formula. You can solve for any of those three things. If you have the liters and the molarity, which is a very common calculation, you can get the moles, and that's something that you do a lot in chemistry. If you have the moles and the molarity, you can get the liters from that by dividing the two. So those are sort of three ways that you can kind of rearrange this equation to solve for what you're looking for. So I think we left off here at this example. So why don't you take a couple moments here and give it a go. We want to calculate the molarity of a solution that's made from 20 grams of sodium hydroxide in 250 milliliters of solution. I'm going to give you some numbers that you'll need from the periodic table. The molar mass of sodium is 2299. Molar mass of oxygen is 16 grams per mole, and the molar mass of hydrogen 1.008 grams per mole. All right, so why don't you take a couple of minutes or so here and calculate the molarity and see what you come up with, and then we'll talk about it and make sure everybody, again, is on the same page. Okay, so let's take a look here and see how we're doing. Um, we want to calculate the molarity of the solution that's made by 20 grams of sodium hydroxide in 250 milliliters of solution. So a reminder that, again, molarity is moles per liter. So in terms of those two numbers, we do have the liters part. It's just in milliliters at this point. So we do have to do that conversion. So we do want to take the 250 milliliters. We want to convert it to liters. And again, a very common conversion that you have to do. We're going to divide by 1,000 so that the milliliters cancel, leaves us with 0.25 liters. Now the top part, which is the moles, again, we don't have that, but we do have the grams. So we do need to use the molar mass from the periodic table. So that basically is adding all those together since we have one of each. And if we add all those numbers there together, we end up with, let's try that again. We end up with pretty much 40 grams per mole. And again, we're going to use that from the periodic table as a conversion factor. And that would mean that we would take our 20 grams of sodium hydroxide, we would divide it by the molar mass from the periodic table. And that will get us 0.5 moles. And that is the top part that we need. So now that we have everything that we need for the molarity, we're just going to divide those two. So we're going to take 0.5 moles on top, 0.25 liters on the bottom, and we'll end up with something like 2. And now in terms of the units, you can leave it as moles per liter if you like, or you can just go 2 and write the big M. So either way is perfectly fine. Again, the units don't cancel, but the big M does stand for moles over liters, so you can leave it, whichever way you want. Number always stays with the moles part, and it's always 1 liter, usually on the bottom. Question on that calculation? Any parts of it? Okay, so like I said, molarity is, again, probably the most common unit of concentration that you'll come across. And, calculating molarity is something that you'll do a lot in chemistry. And this kind of use of it as well is something that you'll do a lot, where you'll use the liters and the molarity basically to figure out the mole. So that's a very, very common calculation as well. So again, like I said, you can sort of rearrange this equation and solve for a lot of things, like our volume times the molarity. Again, always when you're using molarity, you want to make sure that the volume is in liters. Uh, Sometimes people have the tendency to want to sometimes just take the volume in milliliters and times it by molarity, which you can do. The difference is when you take liters times molarity, you get what's known as moles. And that's because liters times molarity would be moles per liter. Liters would cancel, and you get moles. If you actually take milliliters times molarity, you don't actually get moles. You get something that's known as millimoles. And that's because if you kind of do that calculation, the molarity is millimoles per milliliter. So the milliliters cancel, and you get what are known as millimoles. So you technically can multiply the molarity by milliliters, but you don't actually get moles when you do that. You actually get what is known as millimoles. And that's because molarity could be expressed as what's known as millimoles over milliliters. And that's because it is the same thing, because the milli on top and the milli on the bottom cancel, and they become moles per liter. And that's usually what we think about in terms of sort of molarity is moles per liter. But technically you can multiply it by the milliliters, but technically what you're getting is not moles. You're actually getting what are known as millimoles. So if you were to then divide by milliliters, you'll be fine because you'll be back to molarity. But good rule of thumb is just to make sure you convert it to liters so you don't run into any of those sort of issues where you're off by maybe a factor of 1,000 or anything like that. But again, you may see some people multiply milliliters by it. But technically speaking, you're not technically getting moles out. You are getting what are known as millimoles. And again, our rearrangement here on the bottom to solve for volume are liters. So why don't you take a moment or two here and work this one out. What volume in milliliters of a 0.3 molar solution of glucose contains 0.025 moles? So take a minute or so here and calculate that, then we'll talk about it. Okay, so here we're looking for milliliters, which is really a volume. And again, molarity is our moles per liter. So we're really going to be solving for liters. So if we rearrange that, liters would equal moles divided by molarity. Now, when we do have something like 0.3 big M, when you do a calculation, as we talked about last time, it's probably best to break this up into the 2 units. So you can say it is 0.3 moles per liter. You could also use it just like a conversion factor. You can put the liters on top and the moles on the bottom. So I highly recommend sort of converting this big M into those 2 units because it is extremely common that people, for some reason, will leave the big M in their calculation. And really all they focus in on is OM moles. And they forget all about the liters part. They're not sure where it is. Should it divide? Should it multiply? But this way, at least you can kind of see both of the units in the actual sort of conversion factor. And you hopefully can keep track of each of them and sort of use them correctly. So I would recommend when you're doing calculations, like we talked about last time, get rid of the big M and convert it into those 2 units. So what we do have is the moles. So we have 0.025 moles of glucose. And really, you could kind of solve this like a conversion problem, dimensional analysis. We have moles on top, so we would want to use it like this, which is basically dividing by putting it on the bottom. And up on top would go liters. On the bottom would go zero point 0.3 moles. The moles are going to cancel. That's going to leave us with liters. And we end up with, looks like 0.0833 liters, which is close to what we're looking for. But again, a very common sort of conversion with solutions is liters to milliliters, milliliters to liters. So here, again, 1 liter is 1,000 milliliters. So the liters will cancel. We're going to move that over 3 places to the right. Going to give us 83.3 milliliters. Any questions on that calculation or how to do it? And again, like I said, I would definitely recommend, converting the big M into the 2 units so that you can actually clearly see the units and again see if something's canceling and something's not canceling. Any questions on that molarity there? Or how to calculate the volume from molarity? So the next very common thing that is done with solutions in terms of concentration is a process that's known as dilution. And in a process known as dilution, essentially we're going from what is sometimes referred to as a stock solution to a diluted solution. And really a stock solution is a more concentrated solution down to a diluted solution. And typically in this process, the only thing that you basically do is basically you add more solvent. Again, not 100% of the time, but a lot of times the solvent is water. But again, it doesn't always have to be water. But when you do dilution, really the only thing that you're changing is essentially, you're adding more water. So it's kind of like, the big gulp drink that you get, say, before class with all the ice. It tastes pretty good. You go to class and then, a few hours later, you get back to your car and all the ice is melted, right? And you go and drink the drink because, you're thirsty. And you go, that does not taste as good as it did before. And that's because basically what happened, right, is all that ice melted, added more water, and basically diluted down kind of your more concentrated soda that you had. And that's basically the same idea. If you think about it, the amount of sort of soda that you had in there originally, still the same, right? The only difference is you added more water to it. So you may have a little bit more volume, but that volume was made up of basically the ice making, melting and making the water. So in a dilution, what happens is the moles of the solute, which is the smaller part of the solution, remains the same. The only difference is you add more solvent or more water to it. And you can see that here. So if you look at these circles, for example, if we count them, there's 2, 4, 6, 8, 10 on the left, 2, 4, 6, 8, 10 on the right. So the little circles are our solute, remains the same on both the left-hand side and the right. The only difference is the volume here of the solution increased. And what that's going to do, if you just think about molarity in general, molarity technically is the moles of solute, write out all the words there, liters of solution. So since the moles of solute remains the same when you do a dilution, but the volume increases, what you're essentially doing in a dilution is you're increasing the bottom part here. And if you increase the bottom part, you're basically going to take a small number divided by a larger number. And what's going to happen to your molarity is going to go down in a dilution. Again, because the bottom number here gets larger, which means the overall molarity will get smaller. So there actually is a dilution equation. It's on the bottom here. It's M1V1 equals M2V2. And M1 is molarity, M2 is molarity as well. So sort of a before the dilution and after the dilution type of deal. M1 again and M2 are molarity. V1 and V2 are obviously volume. And this is also kind of before and after. So when we do a dilution, for example, and you use this equation, this is an equation where you actually can, if you want, leave the volume in milliliters. It's okay. Yeah. Again, because we have molarity and volume on both sides, you actually can leave it in milliliters. Because as we were just talking about, when you would multiply, say, the left together, you would get millimoles. And then if you divided by the right-hand side, that's in milliliters, you'll come back to molarity as well. Or you can convert them to liters too. So this one is okay either way. You could go milliliters or liters in this one. Again, if you're more comfortable, you can convert it to liters, but you can actually leave it in milliliters in this particular formula, and everything will work out okay. The only difference is if you had V1 as milliliters and you solve for V2, it would be in milliliters. If you did V1 in liters and you're solving for V2, it would be in liters. So it's okay in either unit. Sometimes you'll see this equation in a more generic sort of form, and sometimes people will use this equation as C1V1 equals C2V2, and it's really the same thing, except that the C here is just generic for concentration. And this could be technically something like percent mass to mass that we talked about. You could do percent volume to volume. You could do like percent mass to volume, etc. It doesn't necessarily always has to be molarity, although most people will use the M1V1 equals M2V2 because, again, molarity is that most common unit of concentration. But technically speaking, you don't have to use molarity in that sort of formula. So sometimes people will write that equation more as a generic way as C1V1 equals C2V2. Works the same way and so forth. Typically, when you solve for V2, that is your final volume. V1 is typically the volume of your more concentrated solution. And obviously M1 is the molarity of your more concentrated solution, and M2 is usually the molarity of your less concentrated solution. So why don't you take a second here and calculate what we're looking at here. What is the concentration or molarity of a solution that's formed by diluting 5 milliliters of a 3.2 molar glucose solution to, that shouldn't be 40 milliliters, should be a dash there. 40 milliliters of the solution. So take a second and calculate that. Okay, so let's take a look here. So again, this is a dilution type problem. We're diluting it down. So we are going to use M1 V1 equals M2 V2. And again, you could kind of go in order. You could the most concentrated one. So our M1 here would be 3.2 molar. Our V1 would be 5 milliliters. Our V2, which is our final volume in our more dilute solution. And here we're really looking for M2. So in this case, we would rearrange this and solve for M2. And M2 would equal M1 V1 divided by V2. Again, in this case, we can leave the volume in milliliters, or if you want, you can convert both of these volumes into liters. It's perfectly fine, which if you did, you would have something like that. And if you converted this into liters, you would have something like that. But again, you can leave it in milliliters. I'm going to show you why again here in this particular formula it's okay. So if we take our 3.2 molar, we times it by our 5 milliliters divided by our 40 milliliters. The reason why, again, it's okay, as we talked about, is you can actually just see here, milliliters and milliliters are going to cancel when they divide, and you will be left with molarity. And that's, again, because technically in this case, you're taking molarity times milliliters on top, which gives you millimoles. And then on the bottom, you're dividing by milliliters. So those millis cancel, and it returns you back to molarity, which is big M. So again, in this particular case, if you're using something like the dilution formula, you don't necessarily have to convert it to liters, but you can if you want. You will get the same answer. It's all good either way. But just to be clear, if you're using molarity by itself and you're not doing a dilution problem, you do need to convert it to liters. So just to be clear, if you're doing something where you're taking liters times the molarity, and that's all you're doing, to figure out moles, you do need to convert it to liters for sure. Okay. So if you do all that, we will get 0.4. And again, you can leave it as big M, or if you wanted to, again, you could do it as moles per liter. Either way is perfectly fine. What we do see here, right, is we added more volume. So our molarity, as we went this way, decreased, right? It went from 3.2 molar to 0.4 molar, and obviously the molarity went down. Question on that one. So just so we're clear, if we were to make this actual solution, what we're really doing here is, do like a line right there. All right. So what we're doing here is we basically have a bottle that has a molarity of 3.2 molar of glucose. And basically what we're doing is we're going to take out of that bottle and put into another container 5 milliliters of it. And what we're trying to make in this bottle is a solution that is 0.4 molar and has a total volume of 40 milliliters. So the question is, with that glucose that I just put in there to make this new solution, I do need to put some water in there with it. Do I put 40 milliliters of water in with my 5 milliliters that I've already put in there? And the answer would be, do you add 40 more milliliters plus your 5 milliliters, to make this solution? And that answer is no, because that will give you a total of 45 milliliters, right? Which is not the volume you're looking for. So very common on dilution questions, they ask you how much water you would need to add. So the amount of water can be found by usually taking V2 minus V1. So in our case here, V2 was 40 milliliters minus our 5 milliliters, which we already put in there. means in this particular case, we would need to add 35 milliliters of water. So we would add another 35 milliliters of water. And that 35 milliliters of water plus the 5 milliliters of the glucose we put in there would give us a total volume of 40. And again, if you took that then and gave it a mixy, shaky, maybe not so much shaky, when it would all be mixed together, you would end up with a solution that has a molarity of 0.4. So again, that's a very, very common question that's asked in sort of dilution problems, not necessarily, what's the final concentration, which it does, but a lot of times they'll ask how much water you should add to it to actually make this solution. And again, you can usually find it by taking V2 minus V1, and that usually will give you the difference, and that's usually how much water. Any questions on that? So why don't we try one more here? So let's see. How much volume in milliliters of a 10 molar solution of sodium hydroxide is needed to make, let's see, what I want to make. 1,000 milliliters of a 0.25 molar sodium hydroxide solution. All right, so take a second, figure that out, and then also figure out how much water is needed as well. How many milliliters? All right, so take a moment or two here and figure those out. And then we'll talk about it in just a second. Okay, so same idea here. We're doing a dilution. We're not doing any type of reaction. We're starting with sodium hydroxide. We're ending with sodium hydroxide. The only difference is the molarity is going down. As we can see, it goes from 10 molar to 0.25 molar. So we are going to do our M1 V1 equals M2 V2. In this particular case, our M1 is going to be 10 molar. Our V1 we actually don't know. We do know that our V2 would be 1,000 milliliters. and our M2 would be 0.25 molar. So that allows us to solve for V1, and in this case, V1 would equal M2 V2 divided by M1, and putting that together, that would get us 0.25 molar. Again, here you can convert it to liters if you want, but using this particular formula, you can leave it in milliliters. And here we're dividing by 10 molar. And when we do leave it in milliliters, the molarity will cancel, and it is going to leave us milliliters as our answer. Again, that is the difference when you're using this formula and you convert it to, or you leave it in milliliters. What you get out is milliliters as well. And that gives us 25 milliliters. And again, that is 25 milliliters of our sodium hydroxide solution. So again, visually, what's happening here is we have a bottle sitting on the shelf, and that bottle basically, again, is 19 molar. We want to take out something from that bottle, and what that is basically what we just calculated, which is V1. So basically, that's how much we want to take out and put into our new bottle. So here we would just put 25 milliliters. And again, our new guy wants to be 0.25 molar, and we want a total of 1,000 milliliters. So to figure out how much water we would need to put in there as well, here again, the volume of water would be our V2 minus V1, and that gives us 1,000 milliliters minus the 25 milliliters, which is our V1. And if we do that and subtract, we will get 975 milliliters of water that's also needed to be put in there. So again, with that 25 milliliters, we would take 975 milliliters of water and basically dump it in with it. Again, give it a mix, and shake. And again, we would end up with a solution that has a concentration of 0.25 molar. So again, it's a very common question, especially in dilution problems. Not necessarily always what's the final molarity, what's maybe the final volume, but a very, very common sort of question, like I mentioned, is that question about how much water you would need to add. Any questions on dilutions? Okay, so let us then talk about some properties that involve solutions. And these are sometimes what are referred to as colligative properties. So colligative properties are properties that really depend on the concentration of the solute and not its identity. Really, colligative properties depend on the number of particles that are in that solution. And it is the number of particles that are in that solution that affect things like properties of solutions like boiling point, melting point, freezing point. So these things are affected by basically the number of particles that are in there. And the idea is, in certain cases, for example, if you had just, say, water by itself, if you had water molecules by itself and you started to heat it, those water molecules, they're pretty much got a clear path to start to evaporate, for example, at its boiling point. Okay. If you take that same water and you dissolve something in it, not just pure water, but something else in it. Now, what happens when you start to heat it, for example, these water molecules no longer have sort of that direct path. They kind of have to zigzag around all these guys. There's a lot of other stuff in that sort of solution that gets in the way. And what ends up happening is, for example, in terms of boiling point, it will sort of elevate the boiling point. And what that means is water by itself would normally boil at 100 degrees Celsius, but you put something in it, put some salt in it, put some glucose, something in there, some type of particles that get in the way of the natural way that the water could escape at the boiling point. and then maybe it boils at 105 degrees, or maybe it boils at 110 degrees Celsius because of that. Same thing with like water, you know, when it comes together to freeze, for example, all those water molecules, you know, they all could kind of come in together with nothing in the way, you know. If you put some salt or rock salt, for example, in there, some other things in the way, again, as those water molecules try to come together to freeze, there's a lot of stuff in the way. So it actually will lower something like the freezing point. So instead of, say, water freezing at 0 degrees Celsius, it will freeze at maybe -2 degrees Celsius or something like that. So the idea here is sort of what happens is because we dissolve some of these solute, we have more particles in these solutions. These particles get in the natural way of things being able to sort of freeze or boil. How the solvent by itself, something say like water, would normally be able to do that. So that's one property, is this colligative property, which is known as boiling point elevation. And basically, if something is volatile, it means that it can go into the gas phase relatively easy. So it's able to escape the liquid phase and jump right into that gas phase, with pretty much not very much of a problem to do that. Something that is non-volatile doesn't really go into the gas phase very quickly. Now, when we talk about the vapor pressure, that's basically the pressure of a gas above a liquid. So the vapor pressure, again, if we have a liquid, at the surface of a liquid, we have guys jumping out of the liquid into the gas phase. We also have guys from the gas phase going back into the liquid phase. So at the surface of the liquid, you have a lot of that back and forth happening. And if something is really volatile, what that means is you have a pretty good rate of people actually jumping out of the solution into the gas phase. And what that means is above the liquid, you'll have a lot of gases. And as we talked about, gases, right, have pressure associated with it. So the more volatile a solution is, the more gas it will generate. And that means you'll have more gas above the liquid part, and it will have a higher vapor pressure. And vice versa, if something is non-volatile, that means, you know, not a lot of guys are coming out of the solution. Most of them are kind of staying in the solution, and you have less gas molecules above the solution part, and you would have a lower vapor pressure. So one aspect of colligative properties was known as boiling point elevation. By having something dissolved in a pure solvent like water, it will increase the boiling point of it. So again, instead of boiling at 100 degrees, it will boil at 105, for example, or something like that. Now, in terms of freezing point, it also works kind of the same way as I mentioned before. Again, the presence of those particles that are in that solution is going to cause the freezing point of a substance to go down. So again, what we're usually comparing here is the pure solvent by itself. So something like water, again, just pure water, nothing else with it, to something that's really a solution. You know, something like sodium chloride, for example. Sodium chloride dissolved in there are sodium. When you dissolve that, you have all these sodium ions, these chloride ions, again, getting in the way of the water coming together to freeze. So it ends up freezing at a lower temperature, as opposed to if you just had H2O in there, right? H2O by itself, there's really nothing in the way of those water molecules coming together, and it would be able to freeze at 0 degrees Celsius. You add something like rock salt or sodium chloride to it, maybe it freezes at -5 degrees Celsius, again, because it takes a little bit longer for it to come together. We're not going to worry about the calculations, and that's really what these numbers are for. So don't worry too much about those numbers. All right, so let's talk a little bit about osmosis and dialysis. The membrane that surrounds living cells is what's known as a semipermeable membrane. A semipermeable membrane allows water molecules and small molecules basically to pass through, but ions and larger molecules cannot. So, you can kind of think of it as, a membrane. It kind of has holes in it, if you want to think about it that way. And just like anything, these holes are perhaps big enough for certain things to kind of pass through. But if you try to put something, that's really big and you try to fit it into that hole, it's not going to be able to pass through to the other side. And that's sort of how a membrane works. It's going to be excluded from that. It won't be able to basically pass through. So when we talk about osmosis, osmosis is the movement of solvent molecules from an area of lower concentration to an area of higher concentration. And that's basically what osmosis is. Yeah. So for example, if you had this sort of container, and in the middle you had a semipermeable membrane, and on one side you had just pure water, on the other side, say you had salt water, right? So what would happen by osmosis is the water molecules, which is lower concentration than the salt water. Salt water would be a higher concentration because it has particles and stuff dissolved in it. The water would flow by osmosis to the side with the salt water. And it would continue to flow until it hit a point which is known as the osmotic pressure. And the osmotic pressure is basically that point that's equal to atmospheric pressure coming down. And basically, it has the atmospheric pressure pushing back down the other way. And that's going to stop the flow of water molecules from one side to the next. So, osmosis, you can kind of think about it as sort of a dilution sort of process. The lower concentration, like water, for example, tries to get over to the other side to sort of dilute down the higher concentration. And again, it will stop at this sort of osmotic pressure. That's where reverse osmosis is. Reverse osmosis is when you have something like this, and you have those water molecules moving across till it hits that osmotic pressure. You basically apply a pressure greater than the osmotic pressure. And what that does, basically coming down this way, is force everybody back the other way. Yeah, so it'll go to the left in that case. And if you have a good filter in there, you can catch all the stuff you don't want to go through, and you could end up with no kind of pure water and stuff like that. So through pressure, you kind of force those water molecules. The water molecules would normally want to be going in sort of this direction in my example. But by doing reverse osmosis and applying that external pressure, you're going to force the water molecules actually to travel back the other way. And that's, again, what's known as sometimes reverse osmosis. And again, you can have all kinds of filters and stuff in there that will allow you to capture stuff that you want to kind of get rid of. Here's a much prettier picture of what I've been drawing, but again, here's our membrane. You can see it's basically, holes and channels, and it allows certain size molecules to go through. Obviously, something, say, like this guy here, which looks kind of big, it's going to have a tough time to get through that small hole. And again, it allows sort of filtration to sort of occur. In this case, water molecules over here is going to flow freely, and through osmosis, it's going to basically start flowing from the right-hand side to the left-hand side in a process to sort of dilute down the more concentrated side where it has all these kind of big molecules in it. And again, those big molecules won't be able to go to the other side because they're sort of excluded. And that brings us to a few different types of solutions and sort of the relationship that we talk about. And the first type of solution is what is known as isotonic. Isotonic are basically solutions like we find in IV solutions. They basically have the same osmotic pressure as body solutions. And there's really two solutions that we sort of think of as being isotonic. Is 0.9% sodium chloride and 5% glucose. So these are considered isotonic solutions. And they're sort of the basis solution. When we talk about 0.9% sodium chloride, is sometimes also referred to as a saline solution. It doesn't necessarily have to always be sodium chloride. It could be potassium chloride, something like that. But sodium chloride, saline solution, something like that, 0.92% or 0.9%, and 5% glucose considered isotonic. It means they basically have the same osmotic pressure as body fluids. And what that means, if we take our guy over here, which is our classic example of a red blood cell, RBC, red blood cell. What's going to happen, because there's the same osmotic pressure inside and outside of the cell, what you're going to have is, what that nice picture shows, is basically your red blood cell. Water will flow in and flow out basically at the same rate. And basically what happens is, it's perfectly happy, it's perfectly fine in that situation. Nothing bad's going to happen to the cell if you put it in a isotonic solution. Now, there is a solution which is known as hypotonic, and hypotonic means less than, right? Hypo means less than, basically. And basically what that means is, it has, outside of the cell is less concentrated than inside the cell. So as that pretty picture shows, basically if you take your red blood cell in a hypotonic solution, because the outside is less concentrated than the inside of the cell, by osmosis, all the water in the solution on the outside of the cell is going to rush into the cell. Basically, a red blood cell is a membrane, so allow the flow in and out of solution. And when we have all of that water from the solution running into the cell in hopes of diluting the cell, bad things happen. Your cell kind of swells. Yeah, it gets really big because it's filling up with water, basically, or solution. And basically, it will basically swell. It will burst. And when it does that, that is what is known as hemolysis. So that process of when this sort of red blood cell would burst is known as a process of hemolysis. So that's what we see here. You can see, in comparison to the previous picture, our red blood cell looks like a normal donut, if you will. Here, with all the water, basically our solution running into the cell, it's swelling up like a jelly donut, right? And much like a jelly donut, it will eventually pop, right? You get all that jelly that falls out, right? So the same idea here with your red blood cell, which is obviously not a good situation. There is also a hypertonic solution. And in a hypertonic solution, hyper means more than. And what that means is, the outside of the cell is more concentrated than inside of the cell, right? So what the cell's going to go is, oh, I need to help the outside. So I'm just going to give away all my sort of water and solution, and it's going to run out of the cell. And when water sort of runs out of the cell will start to shrink. And that process of shrinking is what is known as crenation, which also means it's not a great thing. And you get like your donut hole here, right? As it starts to shrink, it gets smaller, basically, it shrivels up. And you get this smaller guy because it's losing all of its water from inside the cell to outside the cell. So how do we know sort of what is what? We can use these numbers that we saw earlier to help us determine, is it hypotonic or hypertonic? So for example, if I put a red blood cell in the following solutions, let's say we put it in 10% glucose. Let's say we put it in 0.4% sodium chloride. Let's say we put it in some water. And let's say we put it in, 5% glucose. So in each of these cases, decide what will happen to the red blood cell. So why don't you take a couple of moments here and try to figure out, if you put the red blood cell into each of these, what will happen to it. So we'll talk about it here in just a second. Okay, let us excuse me. Let us take a look at each of these and sort of figure out what's going to happen to our red blood cell if we put it in there. Let's start with the 10% glucose. So again, these are your two sort of guides to look at in terms of deciding what type of solution. And it is as simple as looking at the numbers. So 5% is isotonic, 10% is glucose is larger than that, which means this would be a hypertonic solution. And in a hypertonic solution, that means that outside of the cell is more concentrated than inside of the cell. And that's going to cause the red blood cell basically to try to dilute the outside. And that's going to cause it to shrink, right? And that is crenation. If we look at 0.4% sodium chloride, again, an isotonic solution is 0.9. So 0.4 is less than 0.9. That means in this case, this would be considered a hypotonic solution. And that means outside of the cell is less concentrated than inside the cell. So that's going to be a case where outside is going to come in because it's going to want to dilute the cell. And that's going to cause the cell to swell, and that's known as hemolysis. Any question on those two? 5% glucose is 5% glucose, which means we're going to get this situation right here. That is going to be isotonic, and the cell will be fine. It'll be a happy cell in that case. Water is going to flow in and out of the cell at an equal rate, and the cell should be perfectly fine. Any questions on those first three? Our last one is water. Now, water is actually a hypotonic solution. So people think water, hey, it's water, it can't be bad. But if you have pure water, basically it has nothing dissolved in it. It basically has an osmotic pressure of 0. Yeah. So it has an osmotic pressure of 0 because it has nothing dissolved in it. So it's actually hypotonic to a red blood cell. And that means that outside of the cell is less concentrated than inside. You would actually get the swelling to occur here. Any questions on that? All right, so again, as you can see, those two numbers here on the screen are important to know because, again, those are basically your baseline numbers to figure out, is your solution hypotonic, is your solution hypertonic, is your solution isotonic. Any questions on that there? Okay. So in the body, blood is filtered through the kidneys through a process known as dialysis. And dialysis sort of works similar to osmosis. It basically allows certain size molecules to be sort of filtered out. So our kidneys sort of help us get rid of waste products like urea and stuff like that. We get it's eliminated in terms of in urine and stuff like that, and helps sort of filter out our body of those type of things. Um, when a person's kidneys are incapable of doing that, then they obviously go through a process known as sort of dialysis, where a machine sort of does that for you. So that kind of filters out sort of the waste products, if you will, and then kind of puts it back in. As you can see, kind of goes through the machine, kind of does the dialysis part for you, gets rid of the waste products, and then it kind of goes back into your system. All right, any questions on any of those things there? That should wrap chapter 8, I think. Any questions on chapter 8? Okay, we're then going to go to chapter 9, I believe. The notes should be up online. Just give me a second here to find it. Okay, here should work. Oh. So chapter 9 here is, hang on one sec. I think I like that. Let's try this one then. Okay. So chapter 9 is acid and bases, and we're going to obviously talk about acid and bases in this chapter and some calculation of things like pH and so forth. So let's start with the talk of acids and bases. So acids have a sour taste. They cause litmus paper to change. So typically litmus paper is a piece of paper that you put some solution on. It changes color. And typically if that color, the litmus paper changes to red, so usually it'll start at blue and end up at red. That indicates that the solution is acidic. It will react with metals to form hydrogen gas in a single replacement reaction like we talked about in an earlier chapter. So for example, if we take something like zinc plus some hydrochloric acid, which is HCl, going to come in and kick out the hydrogen. When it does, it makes that hydrogen gas. That's the bubbles that you see kind of form. And again, it will produce that hydrogen gas in that single replacement reaction. Aqueous solutions conduct electricity really well. So strong acids are strong electrolytes, like we talked about. Electrolytes, right, have the ability to conduct electricity. And weak acids are also weak electrolytes, still able to conduct electricity. Bases have a bitter taste. Obviously, you shouldn't taste an acid or base in a laboratory, right? They do feel slippery. A lot of soaps or bases, things like drain cleaner, Drano, that type of stuff. You know, they're basically sodium hydroxide, you know, type of bases. You could actually go to Home Depot, I think, actually, and buy a drain cleaner that's pretty much straight sodium hydroxide. It also will change litmus paper, and again, that litmus paper, if it turns blue, typically indicates basic, and usually go from red to blue. And also you could have strong bases, which are strong electrolytes. They will conduct electricity really well. You also have weak bases that are weak electrolytes. When we did nomenclature, we talked about the naming of acids. Remember, when we name acids, it's all about whether or not there's oxygen. So if there's no oxygen, that is the acids that get the hydro something ic acid. So that's why our HCl, and again, an acid typically will have that aqueous symbol next to it, is why we call it hydrochloric acid. Also a reminder that if it does have oxygen, it will have one of those polyatomic ions. So one will end with ic acid if it ends in 8. So HNO3. NO3 is nitrate. This becomes nitric acid, as we talked about. And if it does have oxygen and the polyatomic ion ends in ite, it will be OUS acid. So like HNO2. NO2 is nitrite. It will become nitrous acid. So just a quick review of nomenclature, like we talked about when we did naming in whatever chapter that was at this point. Okay, so acids, in sort of a basic definition of acids, is a substance that will produce H plus, or hydrogen ions. It is also sometimes in acid-base chemistry, H plus referred to as a proton. That is because hydrogen has one proton, one electron, right? And no neutrons, right? So in order to become positive, it had to lose an electron. Since it doesn't have a neutron, it is left with just a proton. So sometimes, again, H plus in sort of acid-base chemistry is called a proton. Also an important relationship that things are used sort of interchangeably in acid-base chemistry, H plus and H3O plus. This is what is known as the hydronium ion. are basically the same. They both represent basically the acid part of a solution. So H plus is basically the same as H3O plus. And you will see people use one or the other both in chemical equations and also formulas. I personally will probably use H plus most of the time. So wherever I kind of put H plus in a formula or in an equation, you could replace it with H3O plus. Is again going to be basically the exact same thing in here. There are certain acids that are strong acids, and strong acids are strong electrolytes, which means when you have a strong acid, like the nitric acid, it will 100% break apart into ions, into H plus and NO3 minus. And when you have that in solution, this is 100% what you have in the solution. You don't have any of the nitric acid still together as a whole unit. You have the H plus floating around freely, or you have the NO3 minus floating around. But again, you will not find any of those HNO3 units still together in a solution that's a strong acid. And just to kind of illustrate this sort of place where you will sometimes see H plus versus H3O plus. Let's get some of this out of the way here. This is really an equation that shows what is sometimes referred to as the dissociation of an acid, which is a very fancy word for this acid just broke apart, basically. And another way that you could write this equation is you could actually include water in this equation. And when you include water in this equation, you will end up getting not H plus, but you'll get the H3O plus. And you will still get the NO3 minus. So both of these equations are identical to each other. They're both correct. They both show basically this strong acid breaking apart. And again, sometimes people will do it, and that's usually where we generate our H3O plus from, and it's because basically this guy is giving a H plus over. It's sort of implied in the top one, but again, they both represent the exact same thing, and this is why you will sometimes see these guys sort of interchanged in terms of use a lot in acid-base chemistry. These are some strong acids. So HCl is a strong acid, hydrochloric acid, nitric acid, H2SO4 is a strong acid, HBr, which is hydrobromic acid, is also strong. Hydriodic acid is also a strong acid. Perchloric acid, which is this guy. These are also some strong acids. So these are some very common strong acids that we come across. You should be sort of familiar with these, at least these guys here, in terms of them being strong acids. And what that means is each of them, when they're in solution, will 100% break apart into ions. You would have none of those guys together. So same idea. If you had your hydrochloric acid in solution, again, 100% going to break apart into H plus and Cl minus. So again, 100% is what you would have in that solution. Again, makes it a very strong electrolyte, conducts electricity and all that good stuff because it breaks apart into those ions. Now, bases, on the other hand, are substances that are able to produce hydroxide, OH minus, in solution. And that's really sort of the difference between an acid and a base. An acid has the ability to produce free H plus, while a base has the ability to produce free OH minus ions in solution. Strong bases are strong electrolytes, so things like sodium hydroxide, potassium hydroxide. Pretty much if you kind of look at group 1 and 2 on the periodic table, a lot of those guys in this region here, calcium hydroxide, will be where your strong bases will be from. And if you think about what the names of those two groups are, group one is the alkali metals, group two is the alkaline earth metals, and alkaline means basic, really. Yeah. So alkaline earth metals, alkali metals, alkaline means basic, and that's where a lot of strong bases come from. A lot of strong bases will actually have hydroxide in the formula, and that makes them a very strong base. So something like sodium hydroxide, which is a strong base, will again in solution 100% break apart into the sodium ions and the hydroxide ions. There'll be no sodium hydroxide still together in the solution. And again, because it creates a lot of free OH minus, is considered a strong base because of that. Now, there are bases, as we will see, that are not strong bases. So, for example, something like NH3, which is ammonia, is actually a weak base. And ammonia, although it does not have hydroxide in it, ammonia can react with something like water and actually produce hydroxide through this type of reaction. What's going to happen in this case is actually H plus is going to go this way, as we'll talk about. But it's able to produce hydroxide in solution. It's not able to produce anywhere near something like sodium hydroxide can. Sodium hydroxide pretty much just needs to go for a swim, and it's going to 100% break apart into those ions in the hydroxide. Ammonia needs to go find some water, do a little bit of a reaction, and produce hydroxide. And it's more of a what is referred to as a weak base. And, it mainly is this, but it does produce a little of this guy. And because it's still able to produce a little bit of hydroxide, it's still technically considered a base. But it has to do a little bit of work, if you will, to sort of be able to do that. And is considered a weak base because it will not produce as much hydroxide. So what happens when we do a strong acid and strong base reaction together? Whenever you take a strong acid and strong base together, really the fundamental thing that's happening is the formation of water. So if you remember from when we talked about reactions, if you take a strong acid plus a strong base, you basically will get two things. You will get water and a salt. And basically, if you take hydrochloric acid, that's a strong acid, plus sodium hydroxide, which is a strong base. We will make water, which is H2O. And really the water comes from the H plus from the acid and the OH minus from the base. And again, these two guys basically come together to make the water. And what's left is, as you can see, the sodium from the base and the Cl from the chloride, and that makes our sodium chloride, which is our salt. So that's our salt. That obviously is our water. And if you were to do sort of our total ionic equation and break this apart, you would get H plus Cl minus plus sodium and hydroxide. Remember that water stays together as it is a pure liquid. The sodium on this side would work, and the chloride would come apart as well. That would give us our spectator ions, which, if you remember, are the same ions on each side. And that, and that. And our spectator ions would cancel out. And this gives you our net ionic equation, which is H plus from the acid comes together with OH minus from the base. And the fundamental reaction that happens whenever you take a strong acid and strong base is this formation of water. And that's a driving force for a reaction, is that formation of water. And no matter what combination basically of a strong acid and strong base that you put together, the overall reaction, that if you sort of cut down to the heart of it all, the basic reaction is what we see at the bottom, and what it says, the basic reaction is the H plus from the acid, OH minus from the base is going to make water. So that's really the overall sort of reaction is taking place. That's why when we talked about types of reactions, we referred to as acid-base reactions, sometimes as acid-base neutralization reactions, right? And that is because pretty much the major thing that's being formed is the formation of water. So again, that's why they're sometimes referred to as acid-base neutralization reactions. As you may also remember from sort of our conversation about types of reactions, essentially these are also double displacement reactions. Positive, negative guy, positive, negative. The two positive guys switch partners, so H plus and OH minus makes the water. Sodium plus 1 and chloride makes our sodium chloride. So they're really, again, double displacement reactions that occur. So as I jumped the gun there and wrote all that out, but again, that's our total ionic equation. Remember, when we do that equation, we break apart everything but solids and liquids. They stay together, which is why we kept the water together. When we go to the left-hand side and the right-hand side, you should find some ions that look the same. Those are our spectator ions. They're just there to hang out and balance out the charge. And again, what you're left with brings you to your net ionic equation, which is your H plus and your OH minus. Here are a couple of other examples here. Again, nitric acid plus potassium hydroxide, strong acid, strong base. Same thing going to happen really. Again, our double displacement. So our positive, negative, the H plus and the OH minus come together to make the water. The K plus and the NO3 minus come together to make our potassium nitrate in that particular case, which is our salt. For the most part, salts are usually aqueous and soluble, but they could technically be insoluble in a case or make a precipitate. It does depend on sort of the solubility rules, but probably most of the time you will get an aqueous guy. Any questions on that there? So sort of the first sort of early definition of an acid and base was one that was done by Arrhenius. And he did a lot of work with electrolytes. And again, a reminder, electrolytes are solutions that when they break apart in solution, produce ions. And again, he defined an acid as the ability to produce hydrogen ions. So that's really a good way, if you ever see a reaction or equation, and you see on the right-hand side, H plus or H3O plus being produced, probably going to be some type of acidic solution. And he defined a base as the ability to produce hydroxide. So same idea. If you look at an equation on the right-hand side, you see hydroxide there, probably going to be some type of basic solution. So those are the things you could look for. And what we're talking about in terms of sort of an acid and base solution is these things are free. So something that's able to produce some H pluses or H3O pluses, not bound to anything or anything like that, but basically freely floating around in that solution. And same thing with our base, something that's able to produce hydroxide ions that are technically free by themselves, floating around in the solution. And as we'll talk about in this chapter, the amount of free H plus that you have in the solution or the amount of free OH minus that you have in the solution will have an effect on the pH of that solution and whether how acidic it is or basic it is. Questions on that? Okay, so I think we will stop there today. So a couple of things. Obviously, like I mentioned last time, I know on the syllabus, the next exam is scheduled for next week, and it's obviously not going to be next week. I'm thinking that in all likelihood, it's going to be the week of the 25th and probably going to be on the 27th of May. I'm not going to 100% promise that, but I will let you know for sure. But it's definitely going to be the week of the 25th. and it will cover through this chapter here, which is obviously acid and bases. So I believe it's going to cover chapters 6, 7, 8, and 9. And I think it's going to be the week of the 25th. And again, I'm leaning probably to the Wednesday of that week, which will be the 27th. But again, I'll let you know for sure. But for sure, it's going to be on the 25th, and it will cover this. So hopefully we'll get through most of it on Monday. And again, that's why I'm thinking it might be the 27th there when we'll take the actual exam, just in case we have to finish this on Wednesday and stuff like that. Any questions on that, though? But what we will do, since we do have an exam coming up and it's on a few different chapters, just to make sure everybody's sort of keeping up on pace with everything, this coming Wednesday, we will have a quiz, I think. And why don't we do the quiz on chapter, let's do it on chapter 7. I think that was gas laws and specific heat. So there's a good amount of information in that. So why don't we do chapter 7? That should help review some of that stuff, hopefully. So chapter 7 quiz will be next Wednesday, and we'll probably do it like we did last time. We'll have a little bit of a lecture at the beginning. We'll soft lecture early, and then you could kind of go take the quiz and stuff like that for the rest of the sort of period and stuff like that. So exam, which I guess would be exam 3, I think, 2, one of those exams, whatever the next exam is. I think it's exam 3, I think. Exam 3 will be on the week of May 25. I'm thinking it's probably going to be the 27th, but I'll let you know for sure. Next week, which is the 20th, right? May 20th, we're going to do a quiz on chapter 7. And again, that should be gases, if I'm not mistaken, and like specific heat. And that will take place during lecture, yeah? At the end of lecture. At the middle part of lecture, yeah? So we'll lecture a little bit, and then we'll stop early, and then you can go take the quiz. Any questions on any of that stuff happening or what's going on that I can answer? Okay, if there's no other questions, it is Wednesday, so have a good weekend. Yes, I will see you on Monday, and we will continue lecturing. Thank you. You guys have a good day. Thank you. Have a good day, guys. Bye-bye.